What if the planet you're standing on is in the middle of the biggest transformation it has ever made? And you can't feel any of it happening. The ground beneath your feet feels solid, it feels permanent. It feels like it has always been exactly this way and always will be. But that feeling is one of the greatest illusions in the history of living things. Because the Earth is not still. It has never been still. Not for a single second in 4.5 billion years. It is moving right now, shifting, breathing, rebuilding itself from the inside out. And it has a future so strange and so enormous that most human minds simply bounce off it when they try to grasp it. In this video, we are going to go through that future. All of it, from what happens in the next 10 million years to the next 100 million, to the next billion. We are going to talk about oceans that will disappear, mountains that will rise from seafloors, continents that will crash into each other like slow-motion car accidents that take 50 million years to complete. New islands being born right now from the deep ocean floor, a forest so large it makes its own rain, soils being built grain by grain in a process that started before the first tree ever existed, a moon drifting slowly away from us by the width of 4 fingers every single year, and a sun that is quietly and inevitably getting brighter in a way that will eventually change every single thing about this planet. By the end of this video, you are going to look at the ground you walk on completely differently. Because it is not a floor, it is a surface. And surfaces move. Let's start with something that is happening right now, today. In this exact moment, as you watch this, there is a place in the middle of the Atlantic Ocean where the sea floor is being pulled apart. Not dramatically, not with any noise or explosion or warning, just quietly at roughly the speed that a human fingernail grows. 2 enormous plates of rock are moving in opposite directions. And in the crack between them, molten rock is pushing up from deep inside the planet, hitting the cold water, cooling instantly and becoming new sea floor. The Atlantic Ocean is getting wider. Right now, it has been doing this for about 180 million years. When it started, the Atlantic did not exist. There was no ocean between the Americas and Europe and Africa. Those land masses were pressed together into a single enormous continent. Then something in the deep interior of the planet shifted. A crack formed, long and thin, running roughly north to south through the middle of what was then a single landmass. The crack widened, water flooded in, and the land on either side began to drift apart, slowly at first, then settling into the steady, patient pace it still keeps today. The Atlantic Ocean is the result of a crack that formed 180 million years ago and has been getting wider ever since. Every year, it adds about 2.5 centimeters of new seafloor to each side of the mid-Atlantic ridge, the underwater mountain range that runs down the center of the ocean like the seam of a baseball. In another 50 million years, the Atlantic will be hundreds of kilometers wider than it is today. A ship sailing from New York to London would find the journey noticeably longer, as if someone had stretched the ocean while the world was looking the other way. The coastlines on both sides would look familiar from a map. The shapes of the continents would be recognizable. But the distances between them would have grown quietly and without announcement, in the way that the Earth always does its biggest work. Quickly, without announcement, and with complete indifference to whether anything on its surface is paying attention. This is the first and most important thing you need to understand about the future of the Earth. It does not move dramatically most of the time. It moves the way a very old, very patient thing moves, continuously, relentlessly, and at a pace that makes human history look like the blink of an eye. Now let's talk about what is driving this. Because the movement of the plates is not random, it is not mysterious. It is the direct consequence of heat, and the Earth has an almost incomprehensible amount of heat. The interior of the Earth is structured in layers. The thin outer shell, the crust, is the rock you walk on. Beneath it is the mantle, a layer of rock roughly 2,900 kilometers thick that makes up the bulk of the planet's volume. Below that is the outer core, liquid iron and nickel. And at the very center, the inner core, solid iron under pressures so enormous that even at temperatures comparable to the surface of the sun, the metal cannot melt. The mantle, despite being made of rock, is not completely rigid on geological timescales. Under the enormous pressures and temperatures of the deep Earth, rock behaves more like an extremely thick fluid. Over millions of years it flows. Hot rock deep in the mantle is less dense and rises slowly toward the surface. As it approaches the surface and spreads laterally, it cools, becomes denser, and eventually sinks back down. This circulation, called mantle convection, is essentially the same process that moves heated soup around in a pot, just happening in rock instead of liquid, driven by the heat of the planet's interior instead of a stove, and operating on timescales measured in millions of years instead of minutes. The tectonic plates that carry the continents and the ocean floors are riding on top of this slow circulation. They are not self-propelled, they are carried, dragged along by the movement of the mantle beneath them, pushed apart where mantle material rises, and new crust is created, pulled down into the depths where old, cold, dense oceanic crust sinks back into the mantle. This system has been operating since the early history of the planet, though it may have worked somewhat differently in the distant past, when the Earth was hotter and the mantle was less viscous. It will keep operating for billions of years more, because the heat driving it will not run out on any time scale relevant to this story. And because the system keeps operating, the continents keep moving. Africa is moving northward at roughly the same pace as the Atlantic is widening. Australia is drifting toward Asia at a similar rate. Arabia is pushing up into the body of Eurasia, closing what remains of the ancient Tethys Sea. India, which was once an island continent floating in the ancient ocean south of Asia, has been crashing slowly into Asia for the past 50 million years, and the collision is still happening. The Himalayas are the direct result of this collision. When the Indian subcontinent began pressing against the southern margin of Asia, the rock caught between them had nowhere to go but up. It folded, thickened, buckled upward, and over tens of millions of years built the highest mountain range on the surface of the Earth. The peaks that stand there today, Everest, K2, Kanchenjunga, Lhotse, the entire vast high plateau of Tibet are all the product of this slow, ongoing collision, and they are still being built. Not fast enough to see, not fast enough to feel standing at their base, but fast enough that scientists using precise GPS instruments can measure the change year by year. A few millimeters of uplift annually, compounded over millions of years into the highest terrain the planet has ever produced. The roof of the world is still under construction. This is the world you live on. A world where the mountains beneath your feet are still being built by forces that started 50 million years ago and have not stopped for a single day since. Now let's talk about what happens next, because the story of where these continents are heading is one of the most extraordinary things in all of science, and most people have never really heard it told in full. In roughly 10 million years, something large and significant will be gone from the map of the world. The Mediterranean Sea, Africa, is moving north. It has been moving north for tens of millions of years at roughly the pace a fingernail grows, and as it does, it is slowly closing the gap between itself and the southern edge of Europe. The Mediterranean, the sea that cradled some of the oldest human civilizations, the sea that the Greeks and Romans sailed, the sea that connects 3 continents and has been the center of human history for thousands of years, is being slowly, inexorably consumed by this collision. The water is retreating, not dramatically, not in any way you could observe from a human lifetime or even many human lifetimes. But on geological timescales, the Mediterranean is closing. The gap between Africa and Europe narrows. The oceanic crust beneath the Mediterranean is being subducted, diving beneath the European plate in a slow, continuous process that removes material from the sea floor and gradually shallows the water. In roughly 10 million years, the Mediterranean as we know it will be largely gone. Not all at once. The way the Earth does everything, slowly. The sea will shallow. It will fragment into isolated basins. It will leave behind salt flats and dried seabeds, the traces that every sea leaves behind when it withdraws from the world. These traces persist in rock for hundreds of millions of years. Geologists can read the former extent of ancient seas in the salt deposits and evaporite sequences they left behind when they dried. And where the water was, mountains will rise. New mountains folded up from the sediments that spent millions of years accumulating on the floor of the sea. The limestone and clay and sand that sank to the bottom of the Mediterranean over tens of millions of years will be compressed by the collision of 2 continents and pushed upward into a new mountain range running roughly east to west across what is now the Mediterranean basin. These mountains will be built from the bones of the sea. Their rock will be full of the fossils of creatures that lived in the Mediterranean today. The shells of mollusks, the skeletons of fish, the tiny calcium carbonate tests of the microscopic organisms that drift in the surface waters and rain down to the seafloor when they die. Future geologists, if any exist, will crack open rocks in those future mountains and find the record of a sea that used to exist where the mountains now stand. The same thing has already happened. in the same part of the world. The ancient Tethys Sea, which once separated the northern and southern land masses of the prehistoric world, was closed by the same kind of continental collision tens of millions of years ago. Its floor was pushed upward as India drove into Asia. The limestone and shale of the Tethys seafloor became the rock of the Himalayas. Edmund Hillary and Tenzing Norgay, when they became the first people to stand on the summit of Everest in 1953, were standing on rock that was once the floor of a shallow tropical sea. An ocean became a mountain range. The sea floor became the roof of the world. The Mediterranean will become something else. Something we cannot visit. Something that does not yet exist. Mountains, valleys, rivers draining toward new coastlines, ecosystems occupying terrain that is right now underwater. The creatures living in the Mediterranean today, the octopuses threading through rock gardens on the seafloor, the schools of sea bream moving through the clear, warm water of the Western Basin, the loggerhead sea turtles surfacing to breathe in the Aegean, the sperm whales diving in the deep water between Spain and the Balearics. All of them exist in a sea that is already, in the longest possible sense, on its way out of the world. Their descendants, millions of generations removed, will be something entirely different, shaped by entirely different conditions. Some will have moved to other seas. Some will have evolved into forms adapted to the shallower, warmer, saltier remnant waters. Some will have crossed onto land over millions of years of evolutionary pressure, the way the ancestors of today's whales once went from land to sea in reverse. This is not a tragedy. On the time scale we are talking about, nothing that happens to individual species or even to whole ecosystems is a tragedy. It is transformation. And transformation is what the planet has always done. The same process that will close the Mediterranean also opened it. The same forces that will raise mountains from its floor once lowered mountains and flooded them with water. The earth gives and takes back and gives again endlessly, without preference for any particular arrangement of land and sea. Let's go east now, because there is another major geological story happening in a place that most people think of as just a place where earthquakes happen. The Arabian Peninsula is currently pushing into Eurasia. This collision is geologically young. It only really intensified in the last 15 million years or so, but it has already produced significant consequences. The Zagros Mountains of Iran, one of the largest mountain ranges in the Middle East, are a direct product of this collision. They are still rising. The Iranian plateau is being deformed and thickened by the ongoing compression. The complex geology of Turkey, including the North Anatolian Fault that caused devastating earthquakes in the 20th century, is a consequence of Anatolia being squeezed westward by the Arabia-Eurasia collision, escaping sideways like a seed squeezed between two fingers. The earthquakes that regularly devastate parts of Iran, Turkey, and the surrounding regions are not random bad luck. They are the surface expression of deep, ongoing geological work. Every earthquake in that region is a small increment of the same process that is building the mountains and deforming the plateaus. The energy released in seconds by a magnitude 7 earthquake represents a tiny fraction of the energy stored in the rocks by millions of years of slow compression. The Arabian collision will continue. The peninsula will keep pressing north. More mountain building, more seismic activity, more reshaping of one of the most geopolitically significant regions in the world. In tens of millions of years, the geography of what we now call the Middle East will be transformed beyond any recognition possible from today's maps. But this is still just the regional story. The global story is even more extraordinary. Let's go to East Africa. In Eastern Africa, right now, the continent is tearing itself apart. A Rift Valley system runs roughly 3,000 kilometers through Ethiopia, Kenya, and Tanzania, a zone where the crust is being pulled in two different directions and is slowly splitting along the line of least resistance. The East African Rift Valley is one of the most geologically active regions on land. It is lined with volcanoes, some of them among the most active on Earth. It contains a chain of deep lakes, Tanganyika, Malawi, Turkana, that formed as the land sank between the pulling plates. It is crossed by fault systems that produce regular earthquakes, and it is widening by roughly the same pace as the Atlantic, a few centimeters per year. Slowly, quietly, continuously, in roughly 10 million years, the eastern sliver of Africa, the Horn of Africa, and the eastern coastal region will have separated from the main body of the continent. A narrow sea will have flooded the rift between them, starting shallow and salty, like the Red Sea does today, which itself formed by exactly this process, as Arabia separated from Africa. Over millions of years, it will deepen and widen as new seafloor is produced between the diverging plates. In 50 million years, there will be a new ocean in East Africa, full-sized, with its own currents and its own weather and its own deep water ecosystem and its own chain of volcanoes along its spreading center. A sea that does not yet exist is already forming. Its floor is already being laid, one volcanic eruption at a time, in the hot rocks beneath the East African Rift. There is an ocean being born right now, not metaphorically, literally. And you can visit the place where it is being born, the Afar Triangle in northern Ethiopia, one of the most geologically extraordinary places on Earth, where the East African Rift meets the Red Sea and the Gulf of Aden, and where in some places the spreading center comes above water, and you can walk on the boundary between two diverging plates. It looks like a broken, cracked, volcanic wasteland. It is also the birthplace of an ocean. The Earth is not finished making oceans. It never stopped. Now, let's zoom out further, much further, because individual collisions and rifts are just the local details of a much larger pattern that has been repeating for as long as the Earth has had mobile plates. The supercontinent cycle, every few 100 million years, the continents gather themselves together. They assemble slowly and through multiple collisions into a single enormous landmass. They remain assembled for tens or hundreds of millions of years. Then rifting begins, and they break apart again, the pieces dispersing across the globe. Then the dispersal reverses, and they begin to converge again. And the cycle repeats. The most recent supercontinent was Pangea, which existed from roughly 300 million years ago until about 175 million years ago, when the rifting that would eventually create the Atlantic Ocean began splitting it apart. Before Pangea, there was Gondwana and Laurasia, the two pieces of an even earlier supercontinent called Pannotia. Before that, Rodinia. Before that, others whose names are reconstructions from fragmentary evidence, the geological record of the very deep past being increasingly difficult to read. The pattern is consistent: assemble, hold, break apart, disperse, reassemble, over and over, with a rough periodicity of somewhere between 300 and 500 million years per cycle. The question for the future is, when does the next assembly happen, and what will it look like? The answer depends on which oceans are closing and which are opening. Right now, the Atlantic is opening. The Pacific, on the other hand, is closing. Subduction zones along the western margins of the Americas and along the island arcs of the western Pacific are consuming oceanic crust faster than the mid-Pacific spreading centers are producing it. The Pacific is the largest ocean on Earth today, but it is the remnant of an even larger ancient ocean called Panthalassa that once surrounded Pangea. It has been shrinking for 200 million years as the Americas moved west and subduction consumed its floor. If the Pacific continues to close, and there is no geological reason to think it will not, then in roughly 200 to 300 million years, the Americas will have drifted so far west that they approach the eastern edge of Asia. The Pacific Ocean will close. The Americas and Asia will collide. This is one model for the next supercontinent, called Novopangea or Amasia, depending on exactly how the assembly plays out. Under this scenario, the Atlantic remains open or even widens further while the Pacific closes, and the new supercontinent forms on the far side of the world from where Pangea assembled. Under a different model called Orica, both the Pacific and the Atlantic eventually close, with all the continents converging in a region roughly where the Pacific is today. Antarctica moves north toward the tropics. Australia collides with Asia. The Americas collide with Asia from the east, while Africa and Europe approach from the west. Everything ends up in the same general vicinity. A third model, called Amasia, focuses on the tendency of continents to aggregate near the poles and suggests that North America and Asia will converge across the Arctic, with the next supercontinent forming at high latitudes near the North Pole. Each model makes different predictions. Different mountain ranges at different collision zones, different ocean basins persisting in different locations, different climate patterns driven by the new arrangement of land and sea, but all of them agree on the basic outcome. In 200 to 300 million years, the continents will be substantially reassembled, not necessarily into a single piece. There may be two or more large land masses rather than one, but into a configuration dramatically different from today's and much more consolidated than the widely dispersed arrangement of the present. The life inhabiting that world will be the distant descendants of today's life. Separated from us by 200 to 300 million years of evolution, roughly the same interval that separates us from the late Triassic, the time of the earliest dinosaurs. The creatures of that world will carry the deep ancestry of today's organisms in their genetics, but their forms will be as different from today's animals and plants as today's animals and plants are from the creatures of the Triassic. We cannot predict what they will look like. We can only say with confidence that they will exist, because life always exists. It has not failed to exist on this planet for 4 billion years, and there is no reason to expect it to start failing now. What the supercontinent will do to the physical environment of those creatures is somewhat more predictable. Supercontinents create extreme climates in their interiors. The ocean moderates temperature along coastlines, absorbing heat in summer and releasing it in winter, keeping coastal regions from experiencing the most extreme seasonal swings. The further you get from the ocean, the more extreme the climate becomes. The interior of a supercontinent is as far from any ocean as it is possible to be. The interior of Pangea was one of the most extreme terrestrial environments the planet has ever produced. Monsoon rains of extraordinary intensity struck the coasts during certain seasons, while the interior remained one of the driest places on Earth. Temperature swings between summer and winter were enormous by today's standards. The evaporite deposits, the salt and gypsum formations laid down in the shrinking remnant seas of the Pangea interior, record a world of intense aridity and heat in the continental core. The next supercontinent will create similar interior deserts, vast, harsh, hyper-arid regions where rainfall is almost non-existent and temperature extremes are severe. And at the collision zones, wherever two continents press against each other, mountain ranges of extraordinary height and extent. The Himalayas are the biggest mountain range on Earth today because they are the product of one of the most energetic continental collisions in recent geological history. The next supercontinent will produce multiple such collisions happening simultaneously around its perimeter as all the continents press toward the center. The mountain ranges that result could rival or exceed anything on the current planet. And wherever mountains rise, glaciers form. And wherever glaciers form, meltwater runs. And wherever meltwater runs, rivers cut valleys. And wherever valleys form, ecosystems establish themselves in the shelter of the terrain. Mountain ranges create biodiversity. They create habitat variety, from tropical lowlands at the base to alpine tundra at the summit, compressed into a short vertical distance. They force evolutionary divergence, separating populations on different sides of the range and allowing them to evolve independently. The Himalayas are one of the most biologically diverse regions on Earth today, in part because of the enormous variety of habitat they create. The mountain ranges of the next supercontinent will generate similar diversity. New species in new habitats, evolving in the particular conditions created by the specific geography of a world that has not yet been made. Now let's talk about water, because water is the thread that runs through all of this, connecting every part of the story. The oceans cover about 71% of the Earth's surface today. They always have, roughly. Even during the deepest ice ages, when sea levels dropped by more than 100 meters and vast continental shelves were exposed as dry land, the deep ocean basins remained full. The oceans are the dominant feature of this planet's surface, and they have been for as long as the planet has had a surface. The water in the ocean right now is very old. Some of it was released from the interior of the planet in the first billion years of geological history, when volcanic activity was far more intense than today and vast quantities of water vapor were exhaled from the hot interior and rained out into the first oceans. Some of it was delivered from space by comets and water-bearing asteroids that bombarded the early Earth during the period of heavy bombardment in the first few 100 million years of the solar system's history. Exactly what proportions came from each source is still a subject of active scientific research. What is known is that once the water was here, it stayed. The Earth has not lost any significant quantity of its water in 4 billion years. It cycles from ocean to atmosphere, falling as rain, running in rivers, soaking into the ground, returning to the sea. It gets locked into ice sheets and released when the ice melts. It gets subducted into the mantle along with oceanic crust at subduction zones, carried deep into the Earth, and eventually released again through volcanic eruptions. The water cycles through the planet as well as over it. The water you drink today has been through this cycle countless times. It has been ocean, it has been ice, it has been rain, it has been locked in rock 100 kilometers below the surface. It is very old and it belongs to no one era. It is simply the water of the Earth, cycling endlessly as it always has. The future ocean will be different from today's in its geography. As the continents drift, the shapes of the ocean basins change. The Atlantic grows, the Pacific shrinks. When the next supercontinent assembles, most of the Pacific basin will have been consumed, and a new global ocean, sometimes called Panthalassa II, will surround the assembled landmass. The chemistry of the future ocean will also differ from today's. The ocean is not chemically static. Its composition reflects the balance between inputs from rivers carrying dissolved minerals, from hydrothermal vents releasing chemicals from the ocean floor, from the atmosphere exchanging gases, and outputs through the formation of sediments, the activity of organisms, the subduction of material at ocean margins. The pH of the ocean has varied significantly over geological time. During periods of intense volcanic activity, when large quantities of carbon dioxide were released into the atmosphere, the ocean absorbed some of it and became more acidic. The organisms that build shells from calcium carbonate, corals, mollusks, the tiny foraminifera and coccolithophores that form the base of the marine food web, are sensitive to this acidity. When the water becomes more acidic, the chemistry of carbonate dissolution shifts, and it becomes harder for these organisms to build their structures. This has happened before, multiple times. During the Permian extinction, ocean acidification was one of the factors that devastated marine ecosystems. During the end Cretaceous event, it was a secondary stress on top of the immediate physical effects of the asteroid impact. Each time, marine ecosystems were severely disrupted. Each time, over millions of years, they recovered, not with the same species, not with the same communities, but with life filling the ocean again, evolving new forms to exploit the niches that the disruption had emptied. The coral reefs of 50 million years from now will not look like the reefs of today. They will be different structures, built by different organisms, in water of different chemistry, in ocean basins of different shapes. But there will be reefs, because the conditions that make reef building possible, warm, shallow, clear, sunlit water, will exist as long as the Earth has warm, shallow seas. And warm, shallow seas have never entirely disappeared from this planet. The ocean will keep building reefs. The ocean has been building reefs for more than 500 million years, and there is no force in the geological future that will stop it. Now, let's go underground. Because some of the most important work on this planet happens in the dark, below the surface, in places that most people never think about. Beneath the ocean floor, along the mid-ocean ridges where the plates are spreading apart, there are hydrothermal vents, places where seawater seeps down through cracks in the ocean crust, is heated by the magma below, picks up a rich load of dissolved minerals, and is expelled back into the ocean as superheated water, sometimes as hot as 400 degrees Celsius, which would boil instantly at the surface, but remains liquid under the crushing pressure of the deep ocean. Around these vents, in complete darkness, with no sunlight whatsoever, ecosystems flourish. Tube worms 3 meters long, giant clams, shrimp, crabs, fish, communities of organisms that derive their energy not from the sun, but from the chemical energy of the minerals coming out of the vents, a process called chemosynthesis. The base of these food webs is not photosynthesis. It is chemistry. These ecosystems have persisted through every mass extinction in the history of life because the processes that power them, plate tectonics, volcanic activity, the chemical disequilibrium of the Earth's interior, are not affected by asteroid impacts or solar radiation or the rise and fall of oxygen levels in the atmosphere. They are powered by the heat of the planet's interior, and that heat is not going anywhere. The hydrothermal vent ecosystems of the future will exist wherever there are mid-ocean ridges, wherever the seafloor is spreading, wherever hot rock is close to cold ocean water. They will persist as long as the Earth has tectonic plates. They are among the most durable ecosystems on the planet. They may also be among the oldest. Some researchers think life itself may have originated in environments like these. In the chemical richness of hydrothermal systems on the early Earth, life began perhaps in the dark, around vents in the floor of a primordial ocean. And in the dark, around vents in the floors of future oceans, it will continue. Let's go to the surface now, the land surface. Because what happens on the land in the next hundreds of millions of years is equally extraordinary. The soil. A single teaspoon of healthy soil contains more living organisms than there are human beings on Earth. This is one of those statistics that sounds exaggerated but is not. Bacteria, fungi, archaea, protozoa, nematode worms, mites, springtails, earthworms, beetles, and thousands of other organisms live in densities in healthy soil that are genuinely difficult to comprehend. These organisms are not just living in the soil, they are making it. Soil is not simply crushed rock. It is a living material built by organisms over long periods of time and maintained by the ongoing activity of the communities that inhabit it. When a rock surface is first exposed by a glacier retreating, by a landslide, by a volcanic eruption covering the land with fresh lava, it is bare mineral, no soil. The colonization begins with lichens, those remarkable partnerships between fungi and photosynthetic organisms that can grow on bare rock by extracting minerals from it chemically and capturing carbon from the atmosphere. Lichens crack the rock surface, create tiny pockets of organic material, and begin the process of soil formation. After lichens come mosses, which can establish themselves in the thin proto-soil created by the lichens. After mosses come small vascular plants. After small plants come larger ones. After larger plants come shrubs. After shrubs, in the right climate, come trees. And as each successive community lives and dies on the developing soil, the organic matter accumulates. The mineral particles are broken down further. The microbial communities become richer and more diverse. The soil deepens. This process, primary succession, takes hundreds to thousands of years to go from bare rock to developed forest soil. It is happening right now on the fresh volcanic rock of Iceland, on the moraines left behind by retreating glaciers in Alaska and the Alps and Greenland, on the bare limestone of young mountain ranges. The planet is always making new soil in the places where new surfaces are exposed. And deep in the soil, the fungal networks are working. The mycorrhizal fungi thread fine networks of fungal tissue that weave through the soil of almost every forest and grassland ecosystem on Earth, are one of the oldest and most important biological partnerships in the history of life. These fungi form intimate associations with the roots of plants, threading into the root cells and creating a physical interface between the plant's vascular system and the fungal network extending through the soil. The fungi provide the plant with minerals and water accessed from far beyond the reach of the roots alone. The plant provides the fungi with sugars produced by photosynthesis. It is a trade, a mutualistic exchange that has been running for at least 450 million years, since the first plants colonized the land. But the network does more than connect individual plants to the soil. It connects plants to each other. Carbon and nutrients can move through the fungal network between different individual plants, sometimes between different species. Older, larger trees, sometimes called mother trees by researchers studying these systems, can supply carbon to younger, smaller seedlings growing in their shade, and therefore unable to photosynthesize enough to support themselves. The network transfers resources from the haves to the have-nots in a system of exchange that looks, from certain perspectives, like something resembling mutual support. It is not conscious, it is chemistry. But it is chemistry of extraordinary sophistication, refined over 450 million years of co-evolution between plants and fungi, and it is one of the foundations of every forest ecosystem on Earth. This below-ground world will continue to evolve. New fungal species will develop new ways of interfacing with new plant species. The partnerships will deepen and diversify as the surface world changes around them. In the forests of the supercontinent, in the alien ecologies of a world 200 million years from now, the mycorrhizal network will still be there, invisible beneath the surface, doing what it has always done, connecting, transferring, making possible the growth of every tree above it. Now let's talk about forests, because they are one of the most powerful forces operating on the surface of this planet, and most people think of them as passive, gentle things. A forest is not passive. A single large tree, a mature tropical hardwood, a tall Douglas fir, a centuries-old oak, can transpire several hundred litres of water into the atmosphere every day. It pulls that water up through its roots from the soil, drives it up through the xylem of the trunk, passes it through the leaves, and releases it through tiny pores called stomata as water vapor. That vapor rises into the atmosphere, cools as it climbs, condenses around tiny particles, and forms clouds. The tree makes clouds. Multiply that by billions of trees across millions of square kilometers of forest, and you have a system of staggering power. The Amazon basin, 5.5 million square kilometers of tropical rainforest, generates a significant fraction of its own rainfall. The moisture that falls as rain in the western Amazon has already cycled through the forest multiple times on its journey from the Atlantic coast. It falls, is absorbed by roots, moves up through trees, is released as vapor, rises, condenses, falls again. The forest intercepts the rain and returns it to the sky in a loop that has been running for millions of years. This cycle creates what climatologists call flying rivers, vast streams of water vapor moving westward through the atmosphere above the Amazon, carrying as much water as the Amazon River itself, sustaining the rainfall that sustains the forest. The forest is not just a product of the rainfall. The forest makes the rainfall. Take away the forest and the rainfall declines. Take away the rainfall and the forest dies. The two are so deeply interdependent that they function almost as a single system. The tropical forests of the future will operate the same way. Wherever the climate of the next supercontinent allows tropical forest to establish itself, wherever rainfall is sufficient and temperatures are warm enough, the forest will create its own rainfall and sustain itself through the flying rivers it generates. This is not a fragile system. It is one of the most robust ecological systems the planet has ever built. The forests of higher latitudes tell a different story. The boreal forests, the great belt of spruce, fir, pine and larch that runs across Siberia, Canada, and Scandinavia, are among the most extensive forest ecosystems on Earth. They cover roughly 12 million square kilometers, more than twice the area of the Amazon. They store enormous quantities of carbon in their trees, their peat bogs, and their frozen soils. They regulate climate on a continental scale. These forests are not static. They have contracted southward during glacial periods, when the ice sheets pushed the zone of suitable climate toward the equator. They have expanded northward during warm interglacials, following the retreating cold. Right now, at the tree line where boreal forest gives way to Arctic tundra, the trees are advancing north. The boundary is moving. The forest is following the warmth. As the climate continues to change over the coming centuries and millennia, the boreal forest will keep moving. Eventually, in a warmer world, the tree line will reach the Arctic coast. The tundra will shrink. New forests will grow on land that is today permanently frozen, on soils that develop as the permafrost thaws and microbes begin the work of creating fertility from the raw mineral substrate of the frozen north. The Arctic of the future, in a warm interglacial period, or in the warmer climate of a world with higher greenhouse gas concentrations, will not be the Arctic of today. It will be forested, perhaps not with exactly the tree species of today's boreal zone, but with forest. Trees adapted to the long days of the Arctic summer and the long dark of the Arctic winter, standing on what is today tundra and permafrost, in a landscape transformed by warmth. The green will have moved north, and in some places the green will be threatened by dryness. The great tropical forests are sensitive to rainfall reductions. If the rainfall that sustains them decreases below a threshold, the feedback loop can reverse. Less forest means less transpiration, means less rainfall, means further forest loss. The system that has sustained itself through its own water cycling can collapse when that cycling is disrupted. The planet has seen this before. The Green Sahara, the African humid period, lasted from roughly 10,000 to 5,000 years ago. During this time, a shift in the Earth's orbital configuration brought stronger monsoon rains to North Africa. The desert responded with startling speed. Lakes filled, rivers flowed, grassland spread, trees grew. Hippos lived in rivers in what is now the Central Sahara. Crocodiles basked on riverbanks that are now hundreds of kilometers from any water. Then the orbital configuration shifted back. The monsoon rains retreated southward, and the green world vanished in geological terms, almost overnight. The transition from green savanna and woodland to desert took perhaps a few centuries, a blink of geological time. Rapid enough that some of the people living in the region at the time witnessed it within their own lifetimes. As the lakes shrank and the rivers dried and the land they had farmed turned to dust, the bones of hippos lie in dry Saharan valleys today. The rock art that the people of the Green Sahara left on cliff faces shows cattle and swimming humans and animals that have not lived in North Africa for thousands of years. The evidence of the lost green world is everywhere in the desert. For those who know how to read it, the Sahara will be green again. The orbital cycle will return to a configuration that delivers strong monsoons to North Africa. When it does, in perhaps 15,000 years or 50,000, depending on how other factors interact with the orbital forcing, the desert will respond. The seeds that have been dormant in the soil will germinate. The soil microorganisms that have been waiting through the dry millennia will activate. Grasses will spread, then shrubs, then trees in the wetter regions. The green will return. It has always returned. Let's talk about volcanoes, because they are one of the most misunderstood characters in this story. When people think about volcanoes, they usually think about destruction. Explosions, lava flows, ash clouds, devastation, and those things are real. Major volcanic eruptions can be enormously destructive to local ecosystems and, in the case of the largest events, to global climate. But volcanoes are also builders. They build land, they build soils, they build atmosphere. They have been doing these things since the planet formed, and without them, the Earth would be a very different and almost certainly uninhabitable world. The atmosphere itself is partly a volcanic product. Nitrogen, the dominant gas in the atmosphere, was largely outgassed from the interior of the planet through volcanic activity in the early history of the Earth. Water vapor, exhaled from the hot interior in the first billion years, rained out to form the first oceans. Carbon dioxide, a constant volcanic emission, has been part of the atmospheric chemistry for 4 billion years and is a key component of the carbon cycle that regulates the planet's temperature. Without volcanic outgassing, the atmosphere would be depleted. The carbon cycle, which depends on volcanic emissions to replace the carbon that is constantly being drawn down into rock through weathering and biological processes, would eventually come to a halt. The natural thermostat that has kept the Earth habitable through 4 billion years of changing solar luminosity would lose one of its most important inputs. Volcanoes are not just destructive events. They are part of the planet's life support system. The volcanoes of the future will erupt as they always have. The ring of fire, the volcanic chains around the Pacific Rim, will continue as long as the Pacific Plate continues to subduct beneath the surrounding continental and oceanic plates. Iceland will keep erupting and keep growing. The volcanoes of the East African Rift will keep building their cones and eventually contribute to the construction of the new coastline that will form as East Africa separates from the rest of the continent. Hotspots, places where unusually hot mantle material rises in a plume to the surface, melting through the crust and feeding volcanoes, will continue to produce their characteristic chains of islands and seamounts. The Hawaiian Islands exist because the Pacific Plate is drifting northwestward over a hot spot. The Big Island of Hawaii is the youngest and largest island in the chain, the one currently sitting above the hotspot and therefore the most volcanically active. To its southeast, on the ocean floor, a seamount called Loihi is already building itself upward. In roughly 10,000 years, Loihi will emerge above the surface of the ocean as the newest Hawaiian island. A new island is being built right now, underwater, out of sight, piling lava on lava in the dark, patient accumulation that makes islands. In 10,000 years, it will see daylight for the first time. And Yellowstone. The Yellowstone hotspot has been one of the most volcanically productive regions in North America for the past 17 million years. As the North American plate has drifted southwestward over the hotspot has left a trail of ancient volcanic centers stretching across Idaho and Montana, each one marking the former position of the hotspot relative to the plate above it. Yellowstone sits at the current position of the hotspot. The volcanic history of Yellowstone includes 3 supereruptions in the past 2 million years. At roughly 2.1 million years ago, 1.3 million years ago and 640,000 years ago. A supereruption is defined as an eruption producing more than 1,000 cubic kilometers of material. The largest of the three Yellowstone supereruptions may have produced around 500 cubic kilometers, enough ash to bury the entire continental United States under a layer centimeters to meters deep, depending on distance from the source. Events of this magnitude affect global climate. The sulfur dioxide released into the stratosphere forms a reflective aerosol layer that reduces the amount of sunlight reaching the surface, causing global temperature drops that can persist for years. The vegetation disruption from ash fall affects ecosystems across enormous areas. These are genuinely severe events. But even these events are temporary in geological terms. The climate recovered from each of the previous Yellowstone supereruptions. Ecosystems rebuilt themselves. Life continued. The geological record shows disruption and then recovery every time. Whether and when Yellowstone will produce another supereruption is one of the questions that receives the most public attention in discussions of volcanic hazard, and also one of the most difficult to answer. The intervals between the three previous supereruptions were roughly 800,000 and 660,000 years. We are currently about 640,000 years past the most recent one, which is within the statistical range of the previous intervals. But volcanic systems are not clocks, and previous intervals do not predict future ones. What can be said is that the hotspot is still active. The magma chamber is real and present. The geysers and hot springs of Yellowstone, among the most spectacular geothermal features on Earth, are direct evidence of the heat below. The ground above the magma chamber inflates and deflates over years and decades as magma moves and gases accumulate and are released. The system is alive. In geological time, Yellowstone will erupt again. In human time, nobody knows when. Let's talk about ice in its full geological context. The Earth has not always had ice at the poles. For much of the planet's history, it was warmer than today, and the poles were ice-free. The current period of polar glaciation began roughly 34 million years ago in the south, when the Antarctic ice sheet started to form, and roughly 2.5 million years ago in the north, when the Arctic began to develop permanent sea ice and the northern hemisphere glacial cycles began. The formation of the Antarctic ice sheet is directly connected to the opening of the Drake Passage, the gap between Antarctica and South America that formed as the two continents separated. Before the Drake Passage opened, ocean circulation around Antarctica was blocked by the presence of South America, and warm water from lower latitudes could reach the Antarctic coast. When the passage opened, the Antarctic circumpolar current formed, a powerful current that flows eastward completely around Antarctica, isolating it thermally from the warmer waters to the north. Cut off from warm currents, Antarctica cooled rapidly and the ice sheet formed. A narrow gap between two continents changed the climate of the entire planet. This kind of profound global consequence from a relatively local geological change is one of the most important lessons in the entire story of Earth's climate history. Small changes in geography can trigger enormous changes in ocean circulation, and ocean circulation drives climate in ways that affect every corner of the globe. The same kind of pivotal geographic change will happen in the future. As the continents continue to drift, new passages will open and old ones will close. The Drake Passage will eventually close as South America moves further north. New passages may open elsewhere. Each change will reorganize ocean circulation, and the climate will follow. The glacial cycles of the Pleistocene, the rhythmic advances and retreats of the great ice sheets over the past 2.5 million years are driven primarily by orbital forcing, the subtle variations in the Earth's orbit described by the Milankovitch cycles, changes in the eccentricity of the orbit, the tilt of the axis, and the wobble of the axis on a timescale of tens of thousands to hundreds of thousands of years alter the distribution of solar energy reaching different latitudes. When the orbital configuration is right, the high northern latitudes receive less solar energy in summer. The winter snow doesn't melt completely. Year by year, the snow accumulates. The growing snow and ice reflect more sunlight, a feedback that enhances the cooling. The permafrost expands. The vegetation shifts southward. The sea level falls as water is locked in the growing ice sheets. The ice age deepens. When the orbital configuration shifts, the process reverses. More solar energy in summer, the snow melts, the ice retreats, sea level rises, the forests advance, the interglacial begins. We are currently in an interglacial, the Holocene, which began roughly 12,000 years ago as the most recent glacial maximum ended. The orbital parameters suggest that in the absence of other influences, the next glacial period might begin in roughly 50,000 years. As the orbital configuration shifts back toward conditions that historically favor ice growth during a future glacial maximum, the world will look very different from today. Ice sheets, a kilometre thick, will cover Scandinavia, most of Canada, and parts of the northern United States. Sea levels will be over 100 meters lower than today, exposing the continental shelves. The shallow underwater platforms surrounding the continents as dry land. Britain will be connected to mainland Europe across what is now the North Sea and the English Channel. Alaska will be connected to Siberia across the Bering Strait. The coastline of Australia will extend much further into the surrounding ocean. Dozens of islands that are currently separated by shallow water will be joined to nearby continents or to each other. These exposed continental shelves will not be barren. They will be grasslands and tundra, inhabited by the large animals that have always occupied the edges of the ice. In past glacial periods, these were mammoths, woolly rhinos, cave lions, horses, and the early human populations that hunted them. Whatever animals exist in 50,000 years will make the same use of the newly exposed land that their predecessors made of previous glacial exposures. Life fills the space that's available. It always has. It is extraordinarily good at it. Now let's talk about life directly, because everything we have covered, the moving continents, the changing seas, the rising and falling ice, the erupting volcanoes, the shifting forests is the stage. Life is the story being told on it. Life appeared on Earth approximately 3.8 to 4 billion years ago. The oldest confirmed microbial fossils are about 5 billion years old, found in ancient rocks in Western Australia. Chemical signatures of life, carbon isotope ratios that suggest biological activity, have been found in rocks as old as 3.8 billion years. Life has been on this planet for most of its existence. In those 4 billion years, life has survived everything. It survived the late heavy bombardment, a period in the first billion years of the solar system when the inner planets were pelted with an intense flux of asteroid and comet impacts, including objects large enough to vaporize the surface ocean. The evidence suggests life was present before the bombardment and was present after it. It persisted in the deep ocean, perhaps around hydrothermal vents, in conditions that the impacts could not sterilize. It survived the snowball Earth episodes, at least 2 periods, possibly more. Between about 700 and 600 million years ago, when the entire planet may have been covered in ice from pole to equator, with the ocean frozen over and the land buried under glaciers kilometers thick. How life survived is still debated, perhaps in small areas where the ice was thin enough for sunlight to penetrate, perhaps around hydrothermal vents where liquid water persisted below the ice, perhaps in ways we haven't thought of yet. It survived 5 major mass extinction events: the end Ordovician, the late Devonian, the end Permian, the end Triassic, and the end Cretaceous. The end Permian extinction 252 million years ago was the worst. It killed approximately 96% of all marine species and 70% of all land species. It is the closest life has come in 4 billion years to being entirely erased. And yet, after each extinction, life came back. Not immediately. Recovery could take millions of years. Not with the same species. The world after each extinction was populated by different organisms than the world before it. But life came back, diversifying into the empty niches, evolving new solutions, rebuilding the complexity that the extinction had stripped away. Every mass extinction in the history of life has been followed by a radiation, an explosion of evolutionary innovation, as surviving lineages found themselves in a world of vastly reduced competition and vastly expanded opportunity. The end Cretaceous extinction, 66 million years ago, killed the non-avian dinosaurs and roughly 3/4 of all species on Earth. Within a geological eye blink, perhaps 10 million years, the mammals that had been living as small, nocturnal, mostly insect-eating creatures in the shadow of the dinosaurs for over 100 million years had diversified into whales, bats, horses, elephants, primates, and hundreds of other lineages, filling every available habitat on land, in the sea, and in the air. The dinosaurs were replaced. Their roles were taken over by new actors. The ecological play continued with a new cast. The future will contain more extinctions. The geological forces we have been discussing, continental collisions, volcanic events, climate shifts, changes in ocean chemistry, will each, at various times in the coming hundreds of millions of years, push some lineages to extinction. Some of the creatures alive today will not survive the challenges of the geological future, but others will. And from them will come the life of the next hundreds of millions of years. Evolution never stops. Every generation of every organism carries within it the possibility of variation, and those variations, accumulated over millions of generations, produce the dramatic transformations that the fossil record records. The process is invisible on any human timescale, but across geological time, it is one of the most powerful forces operating on this planet's surface. The descendants of today's birds will be as different from today's birds as today's birds are from the feathered dinosaurs of the late Cretaceous. The descendants of today's mammals will be as different from today's mammals as today's mammals are from the tiny shrew-like creatures that scurried beneath the feet of the Jurassic dinosaurs. The descendants of today's insects will fill roles and niches and habitats that don't yet exist, because the habitats are still being assembled by the drifting continents and the shifting climate. Life sculpts itself to fit the world, and in doing so, it sculpts the world. These two processes, geological change and biological evolution, have been in conversation with each other for 4 billion years. Neither one leads, neither one follows. They move together. They have always moved together. Now let's look at the sun, because the sun is not a constant. The sun is a star in the middle of its main sequence, the stable phase of stellar life, during which a star converts hydrogen to helium through nuclear fusion in its core. This process has been going on for about 4.6 billion years, and it will continue for roughly another 5 billion. But the process is not perfectly steady. As hydrogen is converted to helium in the core gradually becomes denser. To maintain the pressure needed to continue fusion, the core contracts slightly and heats up. This gradual increase in core temperature leads to a gradual increase in the rate of fusion, and therefore in the amount of energy the sun produces. The sun is getting brighter very slowly, by about 10% every billion years. Over the past 4 billion years, the sun has brightened by roughly 30%. This means that when the first oceans formed on the young Earth, the sun was only about 70% as bright as it is today. Yet the Earth was not frozen. The geological record of the Archean eon shows abundant liquid water and active hydrological cycles. How? This is a famous puzzle in Earth science, sometimes called the faint young sun paradox. The answer, most researchers think, is that the early Earth had much higher concentrations of greenhouse gases, carbon dioxide and methane, in its atmosphere, which provided a stronger greenhouse effect that compensated for the weaker sunlight. As the sun gradually brightened over billions of years, the natural weathering of silicate rocks gradually drew carbon dioxide out of the atmosphere, reducing the greenhouse effect in tandem with the increasing solar luminosity. The planet kept itself roughly in balance through this coupled geological atmospheric feedback. This self-regulation has worked for 4 billion years, but it has limits in roughly 1 billion years. The sun will be bright enough that even with very low carbon dioxide concentrations, concentrations below the level needed to sustain photosynthesis in most plants. The Earth's surface will be too warm to sustain the complex ecosystems that exist today. The warming will intensify the water cycle. More water vapor in the atmosphere will provide additional greenhouse warming. The top of the atmosphere will warm, and water vapor will rise higher, reaching altitudes where ultraviolet radiation can break water molecules apart. The hydrogen will escape to space. The oxygen will combine with surface minerals. The oceans will begin to shrink. This process will take hundreds of millions of years. It is not catastrophic in any short-term sense, but the direction is clear. In roughly 1 billion years, the surface of the Earth will be dramatically different from today. Hotter, drier, with a thinner ocean and an atmosphere that has lost much of its water content. The complex, multicellular life of today's world will be unable to survive at the surface. What will remain? What always remains when the surface becomes hostile? Life in the deep ocean, life in the subsurface rock, microbial communities drawing energy from chemical reactions, from geothermal heat, from whatever energy sources are available in conditions that complex life cannot tolerate. These communities, sometimes called the deep biosphere, are already present on Earth today. They extend kilometers into the ocean floor and into the continental crust, living at temperatures and pressures and chemical conditions that would instantly kill any animal or plant. Their total biomass may be comparable to all of the surface life on Earth combined. When the surface becomes too warm, they will still be there. They have always been there. They were there before complex life existed, and they will be there after the surface conditions that support complex life are gone. 1 billion years from now, the Earth will still be alive, just differently alive than it is today, and in 5 billion years, the Sun will exhaust its hydrogen fuel. The core will contract and heat up further. The outer layers will expand dramatically. The Sun will become a red giant, swelling to perhaps 100 to 200 times its current diameter. Mercury will be consumed. Venus will almost certainly be consumed. Whether the Earth is consumed or merely scorched from close proximity is still debated. The expansion of the Sun's outer envelope is complicated by the mass loss that accompanies the expansion, and mass loss from the Sun will cause the Earth's orbit to expand outward. But even if the Earth survives as a body, it will be completely transformed. The oceans will have been gone long before. The atmosphere will be stripped or drastically altered. The surface will be a barren, extremely hot rock. And that is the end of this story. But that is 5 billion years away. Everything before it is the story. And the story is extraordinary. Let's come back to the present moment. Stand here for a second, wherever you are. Look at the ground. Feel the solidity of it beneath your feet. Think about what you now know is happening inside it, beneath it, in the slow mantle convection and the drifting plates, and the heat flowing outward from the core. The ground is moving. It is carrying you and everything on it toward a destination it will only reach in tens of millions of years. The ocean basin that lies under whatever water is nearest to you is either opening or closing, adding to itself or being consumed, in a process that has been running for hundreds of millions of years. The air you breathe has been exhaled by volcanoes and processed by photosynthetic organisms and cycled through the atmosphere countless times. The water in your body has been ocean and rain and ice and river and groundwater repeatedly over billions of years. You are made of things that are very old, living on a surface that is constantly being remade, breathing an atmosphere that is itself a product of the planet's biological and geological history. Nothing about this is permanent. Not the mountains on the horizon, not the coastlines on the maps, not the species in the fields or the forests or the ocean, not the configuration of the continents, not the chemistry of the atmosphere, not the brightness of the sun. Everything is in process. Everything is in motion. Everything is transformation, and the transformation is not troubled by time. It is made of time. It is patient in the way that only very old things can be patient. The patience of mountains, the patience of oceans, the patience of a planet that has been remaking itself for 4.5 billion years and has learned through every catastrophe and every recovery that the only direction is forward and the only constant is change. The night is long, the earth is longer, and in the morning, as it has every morning for 4.5 billion mornings, the sun will rise, the light will cross the water, the forest will begin its transpiration, the rivers will carry their sediment toward the sea, the plates will have drifted their daily fraction of a millimeter, and somewhere in the deep ocean, a hydrothermal vent will exhale its superheated mineral-rich water into the cold darkness, and the creatures that live around it will continue doing what they have always done, living, adapting, persisting. The earth turns. The stars move overhead. The moon pulls at the water rises and falls, and the world continues its turning, quietly, without hurry and without end. Now go watch the next video on your screen.